So in our school, there was a test, right? So probably after that, the students will be coming in.
Pardon me?
There was a test in our school till 12 o'clock. So probably after the test is over, the students will be coming in.
Okay, thank you. Yeah, so first of all, I mean, yeah, thanks, Tadashi. It's what, 11:30 there,
yes,
right?
Indeed, yeah. Well, anything for Indian mathematics.
Thank you so much, Tadashi. Yeah, I think these numbers are increasing considerably.
Okay. We are giving a minute or two, is that right?
Yes, so I think we can start and other people can join. Is that okay? I mean, I'll
Yeah, so fine.
Yeah. Okay, so firstly, welcome everybody, and thank you, Tadashi, for sparing time for us at this absurd hour of 11:30 at your time. Right. So, and yeah, so you can already see, I think we are pretty close to the century mark. So since India is a cricket crazy country, centuries are sort of yeah, important anyway. So we'll start with perhaps I mean, I don't think we'll have time for too many questions over and above what has been sent. So I'll start with perhaps the youngest person who, yeah, so we've just reached 100. Good time to start. So maybe we'll start with Shreya. Shreya, can you unmute yourself and ask your question?
Yes, sir. I was asking that if there are two sequences, A1 less than A1, A2, A1, A2, and A1 less than A2, such that, and this way An minus 1 less than An and B1 less than B2, this way Bn minus 1 less than Bn, they are sequences of real numbers, and A1 prime, A2 prime, and this way An prime is a permutation of A1, A2, An. Then A1 Bn, A2 Bn minus 1. This way An A1 is always less than A1 prime B1, A2 prime B2, and An prime Bn. And that one will be less than An Bn, An minus 1 Bn minus 1, A1 B1. Can this be proved using physics, this rearrangement inequality?
Yeah, so let me just sort of translate that for everybody. So Shreya is asking whether there is any physics intuition behind the rearrangement inequality. And Tadashi, go ahead. Yeah.
So I'll recap the question, Ms. Gupta, if I may, in the way that I understood. So let's say that you have three numbers, which are, small, middle, and large, A, B, C, for example, and another sequence of three numbers, alpha, beta, gamma, small, middle, and large in this order, okay? And then you want to combine them, multiply 2 by 2, and try to make the sum as large as possible. For example, you can make them like that. So that's going to be A times alpha, B times beta, C times gamma. So small and small multiplied, middle and middle multiplied, and larger multiplied. So that's one sum. You can add them. Or you can combine them like that. Yeah, you can just reverse, and you say, well, C and alpha are combined and multiplied, and B and beta are multiplied, and A and gamma are multiplied, and then that's you can sum it. So that's going to be, or you can sort of jumble them in any order. Okay. So the question is, how can you combine them 2 by 2 and the sum over so as to make the sum as large as possible, as small as possible, and somewhere in between? That's the question. And the answer is that if you combine them in order, that's the largest, and if you reverse exactly the order, that's the smallest. And anything in between, if you jumble them, so this is the permutation that you mentioned, you get something between this largest and the smallest. Okay, so is there a physical proof of this? Well, first, let's note that this is actually very intuitive, right? Because I don't know if we have this kind of intuition, but if you wanted to have, let's say, even two numbers, A and B, so B is larger than A, and alpha and beta is larger than alpha. Well, how do you multiply them 2 by 2 and add them in order to make it largest possible? Well, this is the largest and this is the smaller. Yeah, this is larger and this is smaller. Well, that's kind of intuitive, I think, because large and large multiplied together will give you something huge, and small, okay, something quite small, but that huge is going to overwhelm anything else that you can produce from the rest. So that's quite intuitive. And this is, there might be some kind of physical argument that derives this. None occurs to me at the moment, and you might amuse yourself inventing one. That's a good exercise. But let's also remark that this is actually very easy to prove. Here's the proof for 2. Yeah, so let's say that, again, B is larger than A and beta is larger than alpha. So how do you know this arrangement inequality? Well, you can say, well, B minus A, which is positive, times beta minus alpha, which is also positive. If you multiply those two differences, that's positive. And you just expand it, and then you get the inequality that, A times alpha plus B times beta is greater than A times beta plus B times alpha. You can get that inequality immediately, okay? And in general, if you wanted to have this for a sequence of n, well, you can just keep sort of switching little by little until you get the right order, or switch little by little until you descend to the completely wrong order, and so forth. So, it's just a repeated application of this. So something that is so near the surface as this rearrangement inequality, somehow we are at a loss as to think of physics, because the physics is something that is, nature prepares a phenomenon and phenomenon happens and so forth. And the point of this exercise is that, well, this phenomenon, we know physically what will happen, but mathematics is a bit more mysterious, but mathematics is really near the surface. So perhaps correspondingly, there's something, as simple as, well, if you multiply two positive differences, well, the product is positive. Well, it really comes to that. So maybe there's a physical interpretation for this this fact, but which, of course, there are plenty, and then you just unpack it in order to get the inequality. So somehow shall I say, if I were to look for a physical interpretation, I would look there, but it's something that is geometrically completely obvious, and so physically there should be something very, very simple indeed. I don't know if that answers the question.
Yeah. Thank you very much, Tadashi. So now we'll go to Ritvik. Ritvik, are you there? You had some question about Pick's theorem in non-Euclidean backgrounds. So would you unmute yourself and ask your question?
Yes, I'm here.
Yeah, go ahead.
Okay, yeah. So my question is about the Pick's theorem. So right, so when we are deriving Pick's theorem from physical arguments, there were two parts, I believe. So in the first part, we essentially concluded that the area of this lattice polygon is the sum of the has two contributions. One is the interior lattice points, and other is essentially the sum of the interior angles over 2 pi. So, and in order to proceed, we needed Euclidean geometry. So my question is, Pick's theorem breaks down in non-Euclidean backgrounds. Is there a physical way of seeing why it breaks down? Let's say in the hyperbolic plane.
Mahan, would you like to say something, or should I answer immediately?
No, go ahead.
Okay. Yeah. So the question, I'd like to look up again, is, sorry, I missed your name. What was your name?
It's Ritvik.
Chakraborty?
Yes.
Okay, good. Okay, Mr. Chakraborty. So, Mr. Chakraborty, if I understood correctly, the question you're raising is about Pick's theorem. I would formulate Pick's theorem a little differently as I did in my lecture, which is that, well, if you have a lattice polygon in Euclidean plane, its area comes from three terms. First, it's not, as natural it is, you count the number of interior lattice points, interior to the polygon, plus half, the weight is half, the number of boundary lattice points, yeah, and then minus one. Minus one is kind of a mysterious thing, but you correctly said, but it comes from the proof, in fact, the physical proof that the latter two terms have to do with adding, angles all over the place and so forth. And Pick's theorem doesn't seem to hold. Well, what about Pick's theorem, let's say, in other geometries? Yeah, where there is some lattice structure. So you might have a discrete subgroup, which has some very regular pattern. For example, in hyperbolic geometry, there is such a thing. In spherical geometry, there aren't so many such things, but that's fine. For example, you can have, say, on the surface of a sphere, you can distribute, let's say, vertices of a regular polyhedron, a platonic solid, which are on the sphere, and then that's as regular as can be, and then it has a lot of symmetry. And if you call that the lattice, well, can you say something about this in this situation and so forth? So I'd like to answer this in two steps. First, you immediately thought about non-Euclidean geometry, but what about Euclidean geometry in higher dimensions? Yeah? Euclidean, but higher dimension, dimension 3, dimension 4, dimension 5, and so forth. And there, in fact, Pick's theorem should work according to the physics, because all you do is, you just prepare, as you recall from the lecture, 1 unit volume of water at each of the lattice points in the entire space, whatever dimension it is, and then flood the entire thing, and you just release it in whatever ambient dimension is. And then you just wait, and there's a symmetry argument, and if you have a lattice polyhedron, let's say, or polytope, as they say in higher dimensions, well, there's a symmetry of the flux, so you can assume that the boundary is impermeable to water, and so on, so on. You can do this. Now, the one place, so the entire world, physics doesn't care how difficult mathematics is, physics works, but at the end, when you try to harvest a nice formula on the mathematical side, there's a problem. The problem is exactly what you alluded to, which is the statement in Euclidean geometry in dimension 2 that the sum of interior angles of an n-gon is n-2 times pi. Yeah? That's because you can just divide it into n-2 triangles. That's no sweat. But there is no such combinatorial formula that gives you the sum of interior angles and so on, maybe other angles and so on. In higher dimensions, that becomes much, much harder. And so this is where the bottleneck is. In order to get something like Pick's formula, you have to go around this bottleneck. And in fact, this has been done in higher dimensions in Euclidean geometry. Indeed, people like Earhart polynomial, and MacDonald, and so on, you should look up those words in Wikipedia elsewhere, Earhart and MacDonald, have higher dimensional generalizations of Pick in the Euclidean case. Okay. What about other, situations where there is some discrete subgroup that gives you a lattice? Well, there is some work in that direction. So Pick actually, or Pick's variation works. For example, Shenson and Capel got a lot of mileage by working on something like Pick's formula, but in toric geometry and so forth. So this works. But you have to be a little careful in non-Euclidean geometry. For example, in the sphere, well, I'm not sure that this is really a good example, but on a sphere, let's think about the points that are distributed on a sphere, North Pole and South Pole, and on the equator, 1, 2, 3, 4 points that form a square. Okay, so there are 6 points, and if you like, those are the vertices of a regular octahedron. Okay, so that looks very regular, and then you want to form a lattice polygon, and presumably each edge of a polygon should be a geodesic in this geometry, so the shortest path, locally shortest path, and so forth. But between, for example, the top and bottom, the 2 poles, there are many, many, many geodesics. And if you draw a geodesic that goes here, 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 well, already the symmetry argument that says that if there is a flux in this direction, there's another flux in this direction, equal and opposite magnitude, and equal magnitude in opposite direction, is no longer so clear. And that's because there are too many geodesics between two given points or to some points, and this is a phenomenon of cut locus. In other words, geodesics is no longer minimizing, so you get a degeneracy and so forth. In hyperbolic geometry, there is no cut locus, so that's fine. We are in better shape, and we should think about it. I will give you the pleasure of thinking, well, in hyperbolic geometry, how should you fix? But there too, there is an a priori problem. The a priori problem is that if you have a polygon, which is a geodesic polygon, so the edges are all geodesics, well, there is a very, very harsh constraint that is imposed on the area by the sum of the angles. Yeah. In Euclidean geometry, because the curvature is 0, that's the constraint comes from something called Gauss-Bonnet, there is no such constraint. You can have many, many, many polygons of different areas, in fact, similar polygons that have the same angles but the different areas. But not in hyperbolic geometry, there's a definite scale that comes from the square root of the, if you like, minus the Gaussian curvature that fits the scale, length scale, so fix the length scale, and somehow you don't have that much freedom. So Pick's formula is a priori in trouble in this case because of this. But you know, there is something that you can do, which I'll give you the pleasure of thinking about. Okay.
Yeah. Okay. Thanks. So by the way, I mean, if I can just ask a follow-up. So you said that you can do something. Maybe you could just drop a hint as to. Do you mean I should probably think about a variation of Fick's formula? I should not be looking for areas of polygons, but something else.
The exact, so that's right. So the exact peak will not work, right? Because of the obstructions that I mentioned. But there's some variations though. And indeed, in a situation where you have some kind of discrete sort of, group and lattice, something can be made to work. But the question is to exercise the imagination to salvage what works and throw away what doesn't.
Okay, thanks.
Yeah. So Ritvik, don't mute yourself because you had another question on the Euler characteristic. Would you like to ask that now? And then we can move to a slightly different topic.
Okay, thanks. Right. So this is about the last example in the talk, the Euler characteristic one.
Yes.
So right.
May I ask who's talking? Can you kind of show yourself or show at least your name? Because
Ritvik, actually you can if you're on video, you can sort of unmute your video also.
That's right.
Okay, I'll try. I'll probably have some bandwidth issues, so I'll follow.
Okay, so in that case, yeah.
Okay, that's right. That's right.
Yeah, it's the same person. Ritvik is asking.
Oh, Chakraborty, Mr. Chakraborty.
Yeah.
Yes. Okay. Yeah, can I go ahead?
Yeah, go ahead.
Okay. Yeah, so I just so could you please, elaborate on the connection between the computation that we did of computing the Euler characteristic of the sphere and discrete Hodge theory? I mean, in general, for let's say surfaces or closed manifolds, etc.
Okay, Mr. Chakraborty, you are picking up on the last thing that I said in the lecture in passing, which is that after we derived we asked nature, in fact, electric circuit, to calculate all their characteristic for, say, Riemann surface with G handles. I said, well, I feel like I'm reinventing the wheel of maybe the discrete version of Hodge theory. And you said, can you elaborate on it? The answer is no, I'm not going to elaborate because this is just an idea. But let me become kind of sort of frank with you and open the cards on the table. It is clearly some kind of Hodge situation because as I said at the time, Hodge theory says that, well, when you consider cohomology, if you like, but cohomology, you don't look at all the possible cycles and you just take the equivalence and so on. But you can, among all the cycles, somehow a canonical one in each class, cohomology class, and that is the harmonic one. And how do you find the harmonic cycle? Well, okay, so you do some kind of minimization in some sense, because whenever you have Laplace's operator that appears, and this is after all, the operator whose kernel is the harmonic objects for any differential form and for anything. Well, Laplacian means that there's some kind of minimization going, the Dirichlet principle, right? So you just minimize something. And what is it that we are minimizing? Well, again, if you revisit the root of the historical root of what Laplace's equation comes from, well, you are minimizing something like the energy, or if you like, the tension and the traditionally it's called action, but it's really energy. So what is it in this case? For example, if you have, say, a torus and you want to find the, let's say this standard torus, so it's kind of the hole in the middle. And if you want to, there are two non-trivial cycles, this cycle and this cycle. And if you want to find those, homology classes, what do you do? Well, in principle, you can just modify them, think of made of rubber, and then rubber can be modified and so forth. As long as it's in the same class, it doesn't matter which cycle you take. But if you want to have the best cycle, well, you suddenly ask the rubber to remember that he's rubber. In other words, he has elasticity, and please shrink as much as possible. And when it keeps shrinking, well, it cannot shrink indefinitely because it gets stuck on something, and the sort of minimum length at which to which it shrunk gives you the harmonic form that is sort of the geodesic, which is here, and geodesic, which is here. So that's how you do it. And in general, you just flow down along, if you like, the functional and the extreme gradient of the functional of some energy. And you put some tension, elastic energy, and you say, well, please shrink, all of you. And then it shrinks, and then where it gets stuck is the harmonic class. Okay. So if you do that in the discrete case, well, why discrete? Because we are talking about dimension 1 and 0 only. That's why it's discrete. If you have something higher dimension, of course, it automatically becomes non-discrete. But in this case, we are talking about the edges and vertices only. So we are working with a graph. So it's discrete, but it's the same thing. You want to have something that's an equilibrium situation. Yeah. So two Kirchhoff constraints that we mentioned. First is the divergence 0 condition, and the second is the curl 0 condition. And I think in your language of Hodge theory, you seem to know too much about Hodge theory, or you're talking about the kernel of the D and the kernel of the dual, if you like, D star. And, okay, so that they correspond to divergence and curl. Maybe it was the other way around. But anyway, so it's exactly Kirchhoff conditions are none other than the historically the most ancient form of the Hodge condition. So clearly it's some sort of discrete Hodge. On the other hand, can you do this, can you push this idea forward and then try to do Hodge theory in any dimension by thinking something like electric circuit? Well, then you start coming really close to the traditional treatment of Hodge theory, because traditional treatment of Hodge theory is just doing, if you like, electrostatics in higher dimensions. Yeah. And so in some sense, it's an idea which is clearly true, but I'm not sure that you can get too much out of this.
Yeah, I was just wondering that, so when I was going through the computations, so it seems that, are we just recovering the fact, so once we have laid down a network on, so for now, let's say a Riemann surface, then you have, so you can consider, so you have a cochain complex, right? So if you consider the vertices
okay, just give me the conclusion. Yeah, just give me the conclusion. Yeah.
Right. So are we just recovering that the index of, the D plus D star is equal to the Euler characteristic?
Well, so sorry, if you say, are we just recovering, you are saying, well, in some sense, is there a logical chain which allows us to see that one thing implies the other and possibly the other way around? And the answer is clearly yes, but that's not the point at all of this approach. Yeah. Because, logical equivalency, yes, the world is full of logical equivalencies, but the surprising thing is that one direction, which people haven't explored so much and which I haven't explored so much yet, and I hope to do so for many, many years to come, really works very, very beautifully in a surprising way, whereas people have been going in the other direction. Yeah. So if you say, well, is it after all equivalent to this and doing that, logically speaking equivalent? Well, sure, almost certainly yes. But is it psychologically equivalent? Is it historically equivalent? And is it, most importantly, scientifically equivalent, which is not the same thing as logically equivalent? The answer is definitely no. It's something new. Yeah. So yes, yes, of course. Yeah. But it's the whole point is the point of view is different and the attitude is different, and that's why you can extract lots of things that are not otherwise accessible.
Yes. Yeah. Okay. Thanks.
Thank you. Yeah, that was very insightful. Okay. Now we'll change gears a little bit and start asking physics people to ask questions. So Arnab, Rudra, you are around? Can you?
Yeah, hi.
Yeah.
Hi.
Yeah. Can you, if you don't have, yeah, there you are. Okay.
Thank you for your nice talk. It helped me to get some beautiful insights of some mathematical, physical insights of mathematical formulas. So I have a very simple question. So the question is that if I understand correctly, that in quantum mechanics, the formulation of quantum mechanics very heavily depends on the structure of Hilbert spaces, right? And operators on Hilbert spaces. So
yes, it's an afterthought.
Sorry?
That's an afterthought. Yes. Okay.
Yeah. So I'm saying if I take the quantum mechanical approach, let's say the approach that Dirac took or the Heisenberg took, then using that, what are the things I can prove on operators and Hilbert spaces in general? For example, equivalence of two Hilbert spaces. Is there some way to think about those questions?
Okay. Yes. Sorry. Thank you, Mr. Rudra. So I shall recap the question as usual. The question is, well, one formulation, I'm going to edit your question. One formulation, one of the many formulations of quantum mechanics, which was invented after actually the ideas of quantum mechanics became clear physically, depends on Hilbert spaces and operators among Hilbert spaces, and then of course the spectral theory and so forth. So can quantum mechanics say something interesting about those things? The answer is in two steps. The first one is kind of the trivial answer. The other one is the more interesting answer. The trivial answer is definitely yes, because in fact, the development of Hilbert space theory and the operators and so on owes a great deal to quantum mechanics. In fact, von Neumann wrote the famous paper, really seminal paper, that set out the entire theory in some sense, as if it came out by parthenogenesis from his own brain, which he did. But he was motivated, of course, by quantum mechanics, and quantum mechanics, of course, led his intuition and so forth. By the way, in some sense, where von Neumann arrived at in terms of the operators among Hilbert spaces is just the end point, not the beginning point. In other words, quantum mechanics is not based on that. Quantum mechanics kind of exists physically, and one way of formalizing it is in terms of this. There are many other formulations, and they are known to be equivalent, more or less. Okay, so this reminds me of, if I insert an anecdote that about von Neumann himself, that during in the beginning of the Second World War, he was of course recruited by Manhattan Project, as you know, and became a great expert on shock waves. More stories to come. But at that time, there was a team of people who really wanted to know something about shock waves, again, part of the war effort, but couldn't ask von Neumann because he hadn't gotten the highest clearance yet. So they had this problem A, but they couldn't really ask von Neumann to work out problem A, the cleverest chap in the field. So what did they do? They worked hard for a week, day and night, transforming problem A to something completely different looking problem B, which nobody could recognize as having come from problem A, and which was nonetheless equivalent to, whose solution would give a solution to problem A. So they brought problem B to von Neumann and said, we are stuck on this, can you help us? And von Neumann said, well, I'll think about it. Next day, von Neumann came back very excited to say, your problem B, I had a wonderful idea. So if you do this, you see, you can reduce this to something much, much more natural, which has a chance of being solved. And that's problem A that they had started from. Okay, so this is a bit like this. Yeah. So yes, if you want to know something about Hilbert spaces and operators, well, please be my guest and just think about quantum mechanics. And of course, there are lots and lots of rich interpretations, and you can amuse yourself. But in some sense, that's not, I think, where the richest sort of hunting ground is. Let me say something else, which I take this opportunity to advertise. People talk about operators and Hilbert spaces, and that's quantum mechanics foundation for quantum. But there's a lot of kind of things that you have to be careful about when you say this. First of all, when you first learn about functional analysis, you learn about compact operators and spectral theory. But compact operators are just peanuts. I mean, among all the operators, linear operators, compact operators are basically zero in infinite dimensional space, right? It actually makes sense to talk about the equivalence of two linear operators on infinite dimensional spaces that are equivalent if and only if they differ by a compact operator. Compact operators are just zero. Okay, so what does it mean to, compact operators basically, and in fact it is a theorem, limits of finite dimensional operators. You're not doing anything new when you're talking about compact operators. Okay. Second, then people talk about the bounded operators. And of course, you know, the entire books on functional analysis are written on bounded operators. But in quantum mechanics, interesting operators are never bounded. Never. It's a theorem because two bounded operators never satisfy Heisenberg's relation. Never. It's a theorem. Well, if they are finite dimensional, you can just trace on both sides and use something wrong because, you know, AB minus BA, trace is 0, equals something proportional to 1, trace is not 0. In infinite dimensions, this theorem doesn't, this proof doesn't work, but something else works. So you can show that, you know, you have to deal with unbounded operators. Now you are in trouble, right? Because most functional analysis books don't go all the way to unbounded operators. They often do. But anyway, so you have to be a little careful. You know, it's not really the paradise that people imagine. Oh yes, Hilbert spaces and bounded operators. No, that's not where quantum mechanics lives. Okay. And finally, let me give you a much better answer to this. There are actually direct applications of quantum mechanical thinking to pure mathematics. And probably the most striking example, it's so striking because both it's so beautiful and trivial, is due to Borchers. So Borchers found a new proof of what is called Jacobi's triple product identity. It comes from theta function. Essentially, you are talking about sum as n, index n ranges over all non-negative integers of something that looks like q to power n squared times z power n. Yeah, so it's a series that involves both parameters q and z. Okay, in q it has sort of squares in the exponent, and in z it has just integers. And this can be factored into 3 factors. Yeah, very beautiful, and it has lots and lots of applications. And Borchers found a proof of this by thinking about the number of states of an electron for given energy and particle number. And you just count these, and then off it drops. By the way, energy in question is always of the form n plus half. So this is square well energy, if you like. Yeah. So you know this this kind of thing does happen, and you know, just thinking about, so this is basically Dirac's electron and hole theory, which is quite ancient. And by thinking about this, you can prove this combinatorial, if you like, theta function identity. So that kind of thing really exists. Concrete application of quantum mechanical thinking, which just takes a problem apart. So I find that personally more interesting, because to say that there is a physical idea which can be mathematically formulated and formalized in this fashion, and then afterwards saying, well, does physics say something about this formalization that I arrived at? Well, I don't expect any surprises, but there are really real surprises where you don't expect it, and that's what surprise means after all. So I think that people should indeed learn to think more quantum mechanically, but not in terms of Hilbert spaces and operators, not in terms of Schrödinger equations and PDEs of certain type, not in terms of even Feynman integral, because after all, these were naturally created in order to accompany quantum mechanics, but in completely unexpected places. That's much more exciting. Yeah.
That's actually, yeah, very nice. So, and in fact, actually, you have answered, I think, Arnab's second question. So I'll skip that and go to the next one. This came on the, I did not carry a name, so I'll just formulate this question as it was put up. Are there applications of the renormalization group? Oh, I think this was on YouTube chat. Are there applications of renormalization group to mathematics? So
yes. So the question, if I may repeat, is I think somebody was very excited about the regularization of the renormalization group.
That's right. Yeah,
they should be discussed. Are there, so they should be understood and applied. And it said, well, the good news is they have been understood and applied. Yeah. And the first the regularization. In fact, this goes way back. In fact, it goes back at least to Euler. And in fact, in 19th century, people like Eisenstein and others, you might have heard of the Mittag-Leffler theorem and so on. These are all examples of regularization. So what I mean, and in fact, Weierstrass product and so on, all those. So what I mean, for example, let's say that I don't know if I can be technical, but let's say that you consider the problem of finding the fundamental solution of Green's function for the Laplacian. Yeah, what can be more physical than that? It's really fundamental. And on the plane, we know, in all dimensions, we know, in dimension 2 is log r, and in dimension d, it's 1 over r2 d minus 2. Okay. And by the way, even the log r thing can be obtained from the other dimensional things by perturbing the dimension, and then taking the limit as d goes to 2, and it's just a regularizing, so to speak. It's a regularization on the regularization problem. But anyhow, we know it for the Euclidean place. But what about other manifolds? Well, for example, in the simplest case, let's say you take the plane, Euclidean plane, which you imagine as standing vertical, and you wrap it up into a cylinder. Okay, it's S1 cross R, if you like. So it's natural to do the following thing. So let's say you have a source which is at a single point, then that source is going to give you something like 1 over, so log R potential. Yeah. And maybe it's better to think about the complex numbers log Z potential. Okay. And you just take the real part later on if you like. Well, if you have a cylinder, that is the same as periodizing in the horizontal direction. Yeah. So you look at, if you like, a pole, not only at Z, but Z plus, plus or minus n for all n. And so you sum over n, and what you are summing over is log of Z plus n for all integer n. Well, this diverges, okay? And so it doesn't get you anywhere. However, you can force it to converge by subtracting off a divergent constant series. What's the motivation for that? Because you see, what we are finding is Green's function, and if you like, the potential. And potential has physical meaning only upon being differentiated. The only thing that has physical significance is the derivative of this thing. So constant term added, subtracted doesn't really matter. Yeah, you can just take freedom. Yeah, so you can subtract off any constant, in particular subtract off divergent. In this case, what you should subtract off is sum of log n. And then it still doesn't work because you get something like a sum of log of 1 plus z over n. But if you now pair n positive and negative and consider log of 1 plus z over n plus log of 1 minus z over n, that's good news, because now you get the sum of log of, now inside log is 1 minus z squared over n squared, and that's conversion. Okay, so that's how you can get that. And this is the really simplest and historically very, very important example of regularization. So this goes all the way back. So please don't believe that regularization has never been studied and hasn't been applied physics. It's all over the place, of course. And anybody who has done complex analysis has met it already a number of times and elsewhere. Okay, about renormalization. Renormalization comes in 2 flavors. They are related, but they are not quite the same thing for that. So one of them comes from QFT, as you know. So this is the renormalization technique that renormalized, for example, quantum electrodynamics, historically the first QFT, and then later on, Hooft and so forth, it proved that Young-Mills is renormalizable in that sense. Okay, so this is kind of shoving infinities under the carpet, that kind of renormalization. The other one is the renormalization group approach, and this is, if you like, it's more like the renormalization semi-group approach. But anyway, you find the fixed point and you try to see how the system, as you scale larger, smaller, and smaller, how the system behaves under scaling, and you can extract some exponents, that kind of thing. So this goes back again long time, but probably the person who made it, it's probably fair to say, made it really the centerpiece of contemporary physics, Ken Wilson, got the Nobel Prize for this, and who started applying it wholesale to statistical physics and condensed matter physics and so on. Okay. Now, renormalization group approach, so let's talk about that, has been tamed, and in fact, it has lots and lots of scientific applications. And in particular, I'd like to mention one. Russians were very quick on the uptake. As soon as Wilson's theory came up, and they started thinking about the renormalization group, and I forget when, but very quickly, a renormalization group approach, proof of the central limit theorem was found. And roughly speaking, what you do is, when a central limit theorem, you have IIDs and independent identically distributed and random variables, which you sum up and you sort of shift by some common mean and then scale by square root of n times the standard deviation and so forth. And you just keep looking what happens. Well, at each step, you go to the next step, and that operator is considered to be some kind of nonlinear operator in the space of random variables. And it turns out that this operator has a fixed point. And that fixed point is the normal distribution, or the random variable that has a normal distribution, but Skorohoti is the same thing. And the wonderful thing is that this is a convergence to the fixed point, and fixed point is an attractor, and that's why central limit theorem is a theorem, and can be understood in terms of renormalization approach, renormalization group approach. So you should look up, if you like, a renormalization group, central limit theorem, and you'll get lots and lots of references. It's a very beautiful approach. I think in textbook, Sefner wrote a nice textbook on entropy in statistical mechanics and information, or something like that, from Oxford University Press. And it's one of the exercises, but it's a doable exercise. And I think he even gives a solution. So you can look up, but there's a lot of literature on this. Yeah? So already in probability, renormalization group has been applied all over the place, and it's a really kind of a well understood and well tamed subject. As for the other flavor of renormalization, I'm not entirely sure that it has had a lot of applications, direct applications to mathematics, in the sense that, of course, it's really a key piece of theoretical physics, QFT, one of the greatest achievements of human civilization, together with the invention of the grand piano. But I'm not sure that it really has. I mean, you know, when people say the impact of, say, high energy physics on geometry, that is all true. You know, it's true. You know, string theory, all that, and so on. But most often, it's really kind of a classical version of, for example, if you say talk about the Young-Mills applied to Donaldson theory, the theory is kind of classical, right? And also you never really compute anything of physical interest. Well, that's a bit of an exaggeration, but it's again, you know, you don't really see renormalization being practiced. It's really more the formalism of QFT that has been useful. So it may be that there is something to be done there, but I'm not immediately aware of anything striking, at least so striking that it has some elementary consequences. But renormalization group, definitely yes. Regularizations of all kinds, definitely yes.
Thank you, Tadashi. And yeah, so the next thing is on behalf of some string theorists who actually, this is essentially, so the driving engine of, we do have time for one question after this, or?
Yeah. I'm fine.
Okay. So the thing is, so ADS-CFT has been this engine of string theory for the last
For those of you who don't know, ADS is anti-de Sitter, CFT is conformal field theory. Okay.
Yeah.
And the correspondence, great. By the way, I was in the same year as Juan Maledacena at Princeton, and we celebrated a PhD at a joint party, and we threw each other into Lake Carnegie. But anyway, never mind.
I see. Okay, very good. So yeah, so have there been sort of implications? I mean, one of the complaints about string theory is that there is no way to experimentally verify it. But there is stuff that comes out, and other sort of concrete mathematical implications, at least philosophically, which mathematicians can now sort of turn the tables and provide experimental evidence to string theorists for. So.
Yeah. So the question, if I understand, is, well, not exactly the concrete instance of ADS-CFT correspondence, but, you know, in general, string theory and high energy physics much more generally has been really closely linked, whatever that means, with the development of geometry and the topology in the last several decades.
Yes.
Really, starting from, we don't know when. I mean, maybe the construction instantons, Schwarz and so on, and also Polyakov, and then maybe Attia and his school. But what is going on? I mean, famously, string theory is way beyond energy levels where experiments can be conducted. But is mathematics going to replace experiment, or what? And also, what are the concrete instances of the string theory being very useful to mathematics, in the sense that, for example, I could use, let's say, pressure in a box in order to prove Pythagoras. Okay. So what is the precise nature there? So there, I think we should ask history. and I'd like to maybe answer questions that were not asked. Mathematics is conducted according to some sociological conventions, and so is physics. But the sociological convention of mathematics is a somewhat weird one. At the time of, let's say, Euler and so on, I mentioned Euler for the second time and for a good reason, they kind of were vaguely confused, right? And healthily confused, shall I say. So they didn't really see the difference between physics and figuring things out in mathematics, figuring things out in physics. It's the same thing. It was about figuring things out and discovering new patterns and making a very coherent connection between them. In fact, one striking example of this is that in modern mathematics, of course, we start from set theory and then even further back, and then we always learn that, well, there are sets and there are maps, and maps always go from one direction to another direction, and one set to another set, and then you have to be careful about the direction, and one point has to go to one point, and you cannot have multivariate maps and so forth. So maps and sets. But Euler never talks about maps and sets. He talks about variables and their relations. So we don't know, where those objects live and in what set it underlies them and so on, but Euler is just manipulating those variables and relations. And it's only at the end of the discussion that their habitat emerges, if at all. Yeah? And that is actually a much more flexible approach to applying mathematics. So I'd like to say the following thing. The contemporary sociology of mathematics is such that you consider a result well established. Well, it's a psychological reassurance, right, of some kind. And I don't mean in a deprecatory manner. I mean, psychological reassurance is what we live for. How do you reassure ourselves that something is established? Well, concept of truth is that you should draw a long chain of logical implications, yeah, whose pedigree goes all the way back to something basic, for example, the Selman-Frankel-Cohen axiomatic set theory or something like that. So that sort of pedigree is what justifies what's above there. Now, there are several problems with this approach, which is that, well, if you have this long chain, and if you cut the chain in the middle for some reason, then everything above it is lost. So it's a very fragile thing. Also, two results, which are, whatever that means, close to each other in some intuitive, some mumbo-jumbo sense, may have to go all the way back to axiomatic set theory and come all the way back. There may not be, you may not see a direct connection between them. It's a bit like the railway system in France. You have to go via Paris, whatever you do. So this is the mathematician's kind of cartoon picture. Of course, mathematics is not really like that, but that's a cartoon picture, and cartoon pictures are very useful. Physics has a completely different worldview, which is that when you have a result, first you want to look at all the results that are in the neighborhood, and you want to connect them in many, many, many ways, as many ways as possible, so as to have a huge local connectivity, such that even if you cut many of those connections, it's still fine, this locally connected cloud is still connected. On the other hand, there might be over there another cloud of related results, and a priori we have no idea whether this cloud of results and this cloud of results are logically connected or not. I mean, if the entire global connectivity is unknown. But local connectivity is very, very, very important for a physicist. Yeah? So these are very different things, very different things. So I would like to say that the way, I mean, I've never worked and in fact I've never quite understood the string theory, and I confess. I studied QFT, but I have lots of good friends who are string theorists and movers and shakers in the string theory. And if I understand correctly, the way they work is that they follow some coherent picture that they have mathematically and some physics and so forth, like Euler. Yeah? And what they really care about the cohesiveness. Local cohesiveness. Oh, this makes sense because it agrees with what we discussed before. And this phenomenon appears here also, and there's so many correspondences and so on. But, they are very vague and confused about, well, whether it can be traced back to Selman-Frankel Cohen system or not. But please remember that ZFC and axiomatic set theory and so on, pedigree or otherwise, is one cultural accident of mathematical history. I mean, there are many, many ways of doing mathematics and many ways of probably organizing mathematics. We just drove ourselves into this corner, if you like. I mean, okay, that's an unkind way of saying. But it's, that's one way that we discovered. It's, if you like, kind of a, formalism that saved the semantics of mathematics. But we know ultimately that even that didn't save mathematics. It's just one way of talking about it. So let's not believe, okay, so of course in mathematics it's very supremely useful to do this make-believe that, sometimes you sort of pretend that I don't know anything about the universe and I have to use those properties only, because that, clarifies our thinking about what are the logical dependencies and so on. But ultimately, mathematics is an organic subject, it's a living creature. And you can try to capture it in some static form by this formalism, that theorem, this theory, and so forth. But these are just our choices. Yeah, and time will pass, and the moods will change, and the fashions will go and come and go. And there will be other formalism, there will be other foundations, but mathematics will live on. So I think the current practice of string theory, mathematically speaking, seems very healthy to me. I mean, it's you just discover new patterns that we didn't discover otherwise. We should be grateful for that. And we shouldn't complain that these are not theorems yet. Well, theorems according to what? In what formalism? Okay, well, I'd rather have new results and new phenomena. If somebody is going to tell me, well, are you willing to sort of bet money or bet your life that this is true according to this and so on, then I might hesitate. But that's another story. But it's true that the mathematics has been rather painstakingly developing a very, very solid sort of approach to life. That should not be neglected either. Yeah. So what is wonderful about mathematics is that when you build, for example, a bridge in engineering practice, well, after so many meters, bridge starts sagging, so you have to put the strut. But in mathematics, and probably in no other human endeavor ever, in mathematics only, you can start building a bridge from the edge of a precipice, and you can build bridges for kilometers and kilometers. And if it's made of mathematics, it will not sag, not by a millimeter, not by a micron. It will be completely straight, and you can very safely walk on it to the end and come back. There is no such way for human beings, human civilization, to control sort of logical and sort of symbolic sort of change of fantastic length and just astronomical, just unimaginable length. And we can control these really precisely. That is a wonderful thing in itself. And so there's that aspect of mathematics which, is kind of cohabits with sort of wild imagination of the string theory and so forth. I think we should cultivate both. And will they meet? Well, so much better if they meet. But even if they don't meet, they sometimes sort of say hello to each other, go further apart. That's okay with me. I'm not in a hurry.
Thank you, Tadashi. So actually, this has led to the last and somewhat philosophical question that had come up again. This is on the questions that had been submitted. And this was essentially a reference to Wigner's statement about the unusual, unreasonable effectiveness of mathematics. Yes. And it was an open-ended question. Do you have something to say about it?
Yes, I have some things to say, but in order not to bore you too much, I'd like to show you a little toy
demonstration. Thank you so much.
I'm known for this. So you can do this in India, elsewhere. What you need is 2 large coins, and then 1 small coin. And in America, I took 2 quarters and 25 cents, silver coins, and 1 small coin, 1 penny, 1 cent. Okay, 2 large and 1 small. Okay, and if I put, you are probably wondering what's the relevance of this to the question. Maybe it's not going to be relevant, but you have fun. All right, so this, if you put the small coin on top of the large coin, okay, and then like so, small on top of the large, and drop them, well, they drop in order. Do you see that? Of course, they drop in order. What do you mean? I mean, top one on top and bottom one on top. Bottom, yes, of course. But now, you should do this at home with your Indian coins. Let me make a sandwich of the small coin between 2 large coins. A tight sandwich, there's no gap, and you put them tight. And then you hold everything together between my fingers. And what I shall do is to release only the 2 bottom ones. Okay, so the middle and the bottom of the sandwich while keeping the top coin between my fingers. Can you see what I'm doing? Okay. And then I try to drop them as horizontally as possible. Yeah. Okay. And what I see is that they flipped over. Do you see that the silver coin, the large coin, is on top of the small coin? I shall do it again if you like. And if you have an iPhone, you can film this with a high-speed camera. Oh, sorry, I dropped the top one, but the bottom 2 have flipped as well. So they automatically flip when you drop. So what is going on? That's quite interesting, right? Okay. I can start start a whole show from this, but let's actually stop here about this. Now, I just demonstrated, but often before I do this experiment, yes, so the sandwich I raised only 2 bottom coins, and then they flipped over again, by the way, they flip over each time. That's very nice. Before I do that, I try to engage the audience and spectators. You know, I might be doing in a theater, I might be doing in a lecture hall, I can be doing in an auditorium. Anyway, so I asked people, guess what's going to happen? You know, guess what's going to happen? You know, I'm about to drop those coins in front of you onto my palm. Those real coins, you know? And what's going to happen? And people often guess, oh, this will happen, and people try to second guess, oh yes, because Tadashi is saying this, that means that something strange is going to happen, and so I'm going to say something strange and so on. But the reaction from my mathematical colleagues is very, very striking. When I'm about to drop those actual coins onto my actual palm and ask them, guess what's going to happen when I do this? Their reaction often is, what are we assuming? And this is a very beautiful professional deformation. You see, we are so trained in the supremacy of logical kind of deductive system that we cannot get ourselves from assumptions. I mean, what do you mean you are living in this particular universe, which is mine, and you have lived here for, I don't know, and I'm about to drop those coins, it's not a conceptual construct, those coins onto my palm, which you can touch. But what are we assuming? And this tells a lot about the cultural, shall I say, the glory and, in some sense, the comedy of mathematics. Yeah. So, about Wigner's unreasonable effectiveness of mathematics and so on. Have you read this essay? The title is very famous, and the thesis is quite interesting. But actually, the essay is not all that well written, I have to say, with due respect to Wigner. So you might be disappointed if you read this essay. But there are many, many other places where mathematics has been unreasonably effective. By the way, you should think about why there has been such an unreasonable ineffectiveness in mathematics in biology. And I have a sort of theory about this, view about this. But anyway, so in physics, it has been very, very effective. But I think it has been effective for the following reason. And that kind of answers addresses the question from the top down. That's because, you know, you remember my picture of a long, long bridge that you can build from the edge of a precipice, and a bridge will be completely straight and completely controllable, and that's what the strength of mathematics is. That's an amazing thing that mathematics does. Yeah, you can keep going for miles and for years and years, and nothing will sag. Well, so mathematics is a very fine and very powerful tool whenever the field or subject has a deep penetration depth. Long penetration depth. If you can keep going for a while, and for some reason, nature arranged physics to have a very, very long penetration depth. You can keep going in physics, and mathematics will come along, and physics will come along, and they'll just keep going, and nothing will sag, nothing will sort of flinch. Yeah. Biology, on the other hand, has a very shallow penetration depth, in my opinion. For example, you know, I've lots and lots of biologist friends, and I'm married to a biologist and so forth. But whenever we talk, and of course I'm interested in biology per se, but whenever I kind of talk cross-culturally, after 2 or 3 steps of argument, they say, "Oh, no, you can't keep reasoning like that because there's an exception, there's a fact, and it's messy, and so forth, so on and so forth." Yeah. So you cannot keep arguing. The argument is not welcome. Yeah. Logic doesn't continue. You just stop and just go back to big data, and then start all over again. Yeah. So I would like to say that biology has seen such an unreasonably ineffective mathematics because biology is too simple, contrary to what people have been saying. Biology is too simple in the sense that it has a very shallow penetration depth. I mean, it has sort of logical diameter of maybe 2 or 3 steps only, whereas physics has a logical diameter of hundreds and thousands of steps. And that, I don't know why that is. That's what nature willed. That's also part of the historical kind of consequence and development of physics, which was, of course, bedfellow of mathematics for a long time. But because of this, mathematics and physics have developed side by side. And now my final answer to this. So I think that they are one and the same thing. Well, it's not quite true because psychological attitudes are different. But again, if we are broad-minded, and flexible and in for amusement rather than sort of straitjacket matinee attitude, I think we can just enjoy figuring things out and discovering new phenomena and patterns and recognizing patterns and then seeing if the same pattern appears somewhere else and if there's something beyond that and so forth. These are both very important and very productive attitudes, both in mathematics and physics. And beyond that, how sociologically we find sort of something publishable, acceptable, and so forth. Well, there two communities diverge, but that's less essential. I think it's just a historical accident, and they come away, come together, come away, come together. This is what friends are like, right? Because good friends, they are not always together. In fact, they can go apart. They're separate ways for decades, and then after several decades, they meet, and then they hit off as they parted yesterday, and so forth. And so it is for mathematics and physics. I think at least nobody is telling us to stick to one or the other. I think we can do both, and it would be really wonderful if more physics can be applied to mathematics, as mathematics has been applied to physics.
That was fantastic. Thank you so much. And this is a wonderful perspective. And I think, so thank you very much, Tadashi. We've already stretched beyond the hour. Yes. And I think it's at least half an hour past midnight at your place. Yes. So thank you very much for giving this time. And we really appreciate all the effort that you put into both your slides and this wonderful discussion. So thank you very much. And people can unmute themselves. And
okay. Have a wonderful life.
Yeah.
Thank you.
Yeah. Goodbye. I'll wait to be disconnected.
Okay.
Out of courtesy.
Oh no, that's okay. You can disconnect if you like. There's somebody who just asked a question. I'll just respond. Yeah, Naveen, can you stop the live cast?
Thank you.
Yeah.
Thank you.
ICTS, are you on? Yeah, I mean, maybe you can just discontinue now. Oh, maybe they've gone for that. So Tadashi, I think it's best if we individually disconnect. Yeah. Okay.
Yes.
Yeah.
So I hope you have a good lunch, by the way.
Yeah. Thank you.
Maybe you had it while this was going.
No, yeah, we will have one, but good night and yeah.
Good night.
Yeah.
Okay.
Yeah.
Take care. We'll keep in touch.
Yeah. Okay.
Goodbye.